Good morning, class 12. You all know that we are discussing the chapter electrochemistry. Now, today we are going to discuss about the variation of conductance, specific conductivity, equivalent conductivity and molar conductivity with concentration or dilution. Dilution means addition of more amount of solvent in the given solution. It means we have to see what happens when the amount of solvent is increased. What happens to all these four? Now keep in mind the electrolytic conductance G, lambda m, that is molar conductivity, as well as equivalent conductivity is directly proportional to dilution. Means when the solution is made more and more diluted, the concentration decreases, hence electrolytic conductance lambda m and equivalent conductivity increases, because with increase in dilution the number of ions increases as the process of electrolysis increases. So keep in mind that electrolytic conductance lambda m and equivalent conductivity is directly proportional to dilution. As dilution increases, these three values increases. Now, on the other hand, specific conductivity, that is kappa, is inversely proportional to dilution, because specific conductivity depends upon number of ions per unit volume. So, as dilution is increased, volume increase, but number of ions per unit volume decreases, because as volume increases, number of ions, it suddenly decreases. As number of particles decreases, or number of ions or number of current carrying particles per unit volume decreases, hence specific conductivity, it decreases with dilution. Now, further we have a very important concept. Now, we are going to discuss about the variation of lambda m, that is molar conductivity, with concentration, or we can say with dilution. Just now we have seen that the molar conductivity, it increases with dilution. There are two types of electrolytes. One is called strong electrolyte and other is called weak electrolyte. The mathematical relation between the molar conductivity at given concentration and the concentration is given by Debye-Huckel-Onsker. This is called Debye-Huckel-Onsker equation, where lambda m is called molar conductivity at infinite dilution. In some books, it's written at zero concentration. If concentration is zero, it means dilution is infinite. And A is a constant, under root C, C is concentration. So, a mathematical relation between the variation of lambda m with the concentration is given by Debye-Huckel and Onsker. By measuring the values of different electrolytes at different concentration, when they plotted a graph, that is lambda m versus under root C, they found that for the strong electrolyte, it is easy to calculate the molar conductance at infinite dilution. But for weak electrolyte, the molar conductance or molar conductivity at infinite dilution cannot be calculated by extrapolation of the graph. Let's see how. Now, this is a graph for a strong electrolyte. They took the value of the concentration under root C versus lambda mc. It has been found that the value of Kc, and this is a strong electrolyte. For example, we can take KCl. Now, the value at infinite dilution or zero concentration. Keep in mind, infinite dilution means concentration is almost zero. So, the concentration 0 or the molar conductivity at infinite dilution can be easily calculated by extrapolation of the graph. Since the graph was coming straight, so it is expected that the molar conductivity at infinite dilution will be this one. So this one is called extrapolation of graph. This is for strong electrolyte, but when they observed the variation of molar conductivity of weak electrolyte, they were quite surprised to see that the molar conductivity of weak electrolyte at infinite dilution cannot be calculated from the graph, as these two lines becomes parallel. So this is for weak electrolyte. You can see that molar conductivity at infinite dilution cannot be calculated, as this line, this curve is not meeting the graph. So to overcome this difficulty, or we can say that to calculate the molar conductivity of weak electrolyte at infinite dilution, kohlrausch, he gave his own view. So this one is known as Onsker-Haeckel, or we say Debye-Haeckel and Onsker view, that is variation of molar conductivity with concentration. Now we are going to discuss Kohlrausch law. Kohlrausch, he simply states at infinite dilution, when dissociation is complete, each ion of the electrolyte has a definite contribution towards molar conductivity. So now let us discuss about Kohlrausch law, the next topic. Kohlrausch law, it simply states at infinite dilution, when dissociation is complete, each ion has a definite contribution towards molar conductivity. So let us start. At infinite dilution, when dissociation is complete, each ion has a definite contribution towards molar conductivity. That is, each ion participate in molar conductivity. Here is the mathematical form. Lambda m 0. In some books it's written lambda m infinity. If we say 0, it means zero concentration. If we write here infinity, then we say infinite dilution. Both have same meaning. So lambda m 0, that is molar conductivity at zero concentration of AX/By, is equal to x be the number of ions of positive, plus y into lambda naught 0, that is molar conductivity of negative ions. Molar conductivity of positive ions plus y into molar conductivity of the negative ions. Let us take a simple case. If we say NaCl, we know that NaCl dissociates into N positive and Cl negative. So lambda m for this NaCl solution can be written as is equal to lambda naught, that is molar conductivity of sodium ions, plus lambda naught molar conductivity of the chloride ions. This is the way. This is known as Kohlrausch law. Now we are going to discuss the applications of Kohlrausch law. As we know that kohlrausch law is used to calculate the molar conductivity of weak electrolytes. But here we have done for strong electrolyte. How we use kohlrausch law to calculate the molar conductivity at infinite dilution for weak electrolyte? That is the next topic. We say applications of kohlrausch law. One of the most important applications of kohlrausch law is to calculate the molar conductivity at infinite dilution for the weak electrolyte. Kohlrausch says if you want to calculate the molar conductivity of weak electrolyte at infinite dilution, in the weak electrolyte add a strong electrolyte which combine with the ions of the weak electrolyte form strong electrolytes. Keep in mind, I'm just writing here, to a weak electrolyte add a strong electrolyte which dissociate completely into ion. Add a strong electrolyte which dissociate completely into ions. So, to a weak electrolyte, add a strong electrolyte which combine with the ions of weak electrolyte to form strong electrolytes. Now, let us see how. Let us take an example of a weak electrolyte, that is acetic acid. So, acetic acid CH3COOH, when it dissociates, it forms CH3COO negative plus H positive ion. It's a weak electrolyte, do not dissociate completely into ions. If we want to calculate the molar conductivity of acetic acid at infinite dilution or zero concentration, we write this way. In this, we have to add a strong electrolyte whose ions combine with CH3COO negative as well as combined with H positive to form strong electrolytes. So, in this case, if we add sodium chloride, sodium plus chloride ions, sodium ions, they combine with acetate ion, form sodium acetate, which is a strong electrolyte. H positive combined with Cl form HCl, which is again a strong electrolyte. If we are adding here Na positive and Cl negative, as we do in mathematics, if we add one thing, we have to subtract the same thing. So, it can be written as minus Na positive minus Cl negative. So, we write here, this one combined with this, it combined with here, and Na combined with Cl, NaCl. So, when we calculate the molar conductivity of acetic acid at zero concentration, that is equal to molar concentration of sodium ion, that is sodium acetate, plus molar concentration of HCl, molar concentration of sodium acetate, molar concentration of HCl. This is a strong electrolyte, this is also strong electrolyte, and this is also strong electrolyte, minus lambda naught of NaCl. It means to calculate the molar conductivity of weak electrolyte, we have to add a strong electrolyte which combine with the ions of weak electrolytes to form strong electrolytes. So, in these type of questions, normally these values are given. We have to just substitute the value and we have to solve the numerical. Now, this is the first application. Now, we have written few more applications of kohlrausch law. The first application that we did to calculate the molar concentration of weak electrolyte at infinite dilution. You can see here the second application is calculation of degree of dissociation. We know degree of dissociation is simply defined as number of particles dissociated divided by total number of particles given. Here, degree of dissociation alpha is equal to lambda mc. That means molar conductivity of the electrolyte at given concentration to the molar conductivity of the electrolyte at zero concentration. It means if we know the value of lambda m0 by using kohlrausch first application, we can easily calculate degree of dissociation, that is alpha. Now the third application, after calculating the value of alpha, we can easily calculate the value of dissociation constant. Here, dissociation constant alpha, K is equal to, now keep in mind this is degree of dissociation alpha and dissociation constant is K. So K is equal to C alpha square upon 1 minus alpha. The value of alpha is lambda mc divided by lambda m0. So K can be calculated easily. After calculating K, the next very important application is calculation of solubility of sparingly soluble salts. Sparingly soluble salts are those salts which do not get dissolved. So their solubility can also be calculated easily by applying a very simple formula. Solubility of sparingly soluble salts is equals to K, that is dissociation constant, into 1000 upon lambda m0, that is molar conductivity at zero concentration or infinite dilution. So we have seen kohlrausch law, we have seen the practical applications of kohlrausch law to calculate various factors. We can calculate alpha, we can calculate K, we can even calculate solubility as well as the molar conductivity of weak electrolytes at infinite dilution. So tomorrow we will discuss about numericals based on kohlrausch law as well as the next topic. Till the time, just revise it. Thank you.